In the last video, we talked about capnography and how it works, and that it uses the Beer-Lambert law of absorption to detect and sense the amount of infrared light that's absorbed in this carbon dioxide sensor as carbon dioxide gets exhaled from the lungs into this detector. In this video, we're going to talk about how this sensor detects the carbon dioxide concentration and how that changes over time throughout the respiratory cycle. So let's begin by illustrating what this graph or this waveform will look like during the very first stage of expiration. So as we expire, most of this, as we begin to expire, right at the beginning of expiration, most of this carbon dioxide, which are represented by these dots, CO2, most of these carbon dioxide particles, let's say, or this concentration of CO2, does not really get to this device or to this chamber here. Most of it is in the lungs. There's some dead space that it needs to get its way to before it makes it to the sensor. So this is, remember, at the very first stage of expiration, we're just beginning to exhale. So because the CO2 has not reached the chamber, it takes time to reach the chamber, we're going to see a low end-tidal CO2 concentration. And like I said, that's because that occupies the areas of the lungs and the breathing tube and not our sensor at that moment. So this next part, once the gas, and I'm going to draw our CO2 here, once the gas reaches our chamber and continues to fill, we're going to start to see a sharp rise in our end-tidal carbon dioxide. That's because the more carbon dioxide that starts to get exhaled, the less light now, the less infrared light is being sensed. So if we shoot 3 photons of light at this point where our carbon dioxide is starting to fill the chamber, then we're likely getting, let's say, again, arbitrarily, we're going to be getting 1 out of it. It's going to start to, this chamber is going to start to have more carbon dioxide, which is going to absorb more infrared light, which is going to reflect in less being sensed at the other end of our sensor. So eventually, there becomes a point where the alveolar gas is sampled and the concentration will reach a plateau. So you only have so much CO2 in your lungs that can occupy this space and occupy this device. So it's not like you'll see this rise going up forever. You'll eventually hit a plateau point when all that alveolar gas or alveolar CO2 gets exhaled and passes through this chamber. So there's going to be a plateau point right over here. And usually at this point right over here at this end, that is where our end-tidal CO2 number shows up. So let's call this, at this point, our end-tidal CO2 is 40. Now after our end expiration, at this point, inspiration usually occurs, and there's a big drop and sharp drop in our carbon dioxide, which I can't really represent here, but there's no more CO2. If this is our sensor, there's no more carbon dioxide that's being passed through, so you're going to get all those 3 photons that are shot at the end of our base plate here, and that is going to reflect as having minimal end-tidal carbon dioxide. So this inspiration causes a pretty big drop in our end-tidal CO2, which senses this fresh gas flow, or the end-tidal CO2, fresh gas flow goes into the system, and there's less carbon dioxide that's in this device now. And that's going to reflect right over here. So we can identify 4 parts to our capnogram. 1, which is the beginning of expiration. beginning, expiration. 2, which is mid-exhalation, or as our carbon dioxide passes into this sensor. 3, right over here, end expiration, and expiration. Eventually all that gas, all that CO2 will end up in this chamber. And then 4 is inspiration. Inspiration. And that is the end-tidal carbon dioxide waveform.